Welcome, everyone. Very pleased to have so many of you with us here today for This Is CDR, an online event series presented by OpenAir to explore the wide range of carbon dioxide removal solutions currently being researched, developed, and deployed, and to contextualize them for policy proposals under development for New York and other states and jurisdictions. Everyone, please feel free to introduce yourself in the chat and tell us where you're zooming in from. I'm Toby Bryce, based in Brooklyn, New York, and I work on CDR policy advocacy with OpenAir. Quick background on OpenAir: we're a distributed volunteer network dedicated to the advancement of carbon dioxide removal solutions essential to solving the climate crisis. Our growing global community collaborates on shared open source missions in the areas of research and development, policy advocacy, and activist market development. We'll put some links to our website and Twitter in the chat. Please follow and join us there. Most of you are familiar with carbon dioxide removal, the practice of capturing CO2 from the atmosphere and storing it safely and for a long period of time in the geosphere, the ocean, and in long-lived products. When considering CDR as we are today and with this series, it's essential first and foremost to emphasize that CDR is not in any way an alternative to reducing emissions. We must reduce global emissions and decarbonize our economy as quickly and as completely as possible, full stop. That said, every credible climate forecast, including in very stark terms the most recent IPCC assessment report, shows that CDR will be required at gigaton scale, that's billions of tons per year by mid-century, to counteract those emissions that are difficult or inequitable to abate, and ultimately to start removing the tremendous excess of anthropogenic CO2 already in the atmosphere so we can restore our climate to a safer and healthier state. If you're new to CDR, our previous This Is CDR sessions are a great place to start. We'll put a link to those in the, to our YouTube channel in the chat, along with a link to the CDR primer, which is a great and comprehensive resource if you really want to dig in to the topic. And of course, we're here today to learn more. So we'll be continuing these sessions weekly on an ongoing basis through the fall. And today we have a great session on direct air capture. Please now meet my OpenAir colleague, Megha, who will introduce today's presenter.
Hi everyone, I'm Megha Raghavan, based in London. I also work on OpenAir's CDR policy advocacy team with a particular interest in the legislative opportunities for California, where I'm originally from. This week, we're very happy to welcome Dr. Habib Azarabadi from the Center for Negative Carbon Emissions in ASU, Arizona State University, to introduce us to direct air carbon capture, or DAC. We'll review current tech pathways and use cases, as well as discuss his influential recent paper co-authored with Dr. Klaus Lackner titled Buying Down the Cost of Direct Air Capture. A couple notes before we begin. So the format is going to be first a 15 to 20 minute presentation, followed by a few prepared questions that we have, and then we'll do some moderated audience Q&A. So if you do have any questions throughout the presentation, please go ahead and type those questions for Habib into the Zoom Q&A box, separate from the chat box, so just make sure you look out for the right Q&A function. The event is being recorded, so we'll send that video link out to everyone who's registered, and also we will post to OpenAir's website and to our YouTube channel. We'll also be live tweeting today's event, so we'll put our Twitter link in the chat if it's not there already, and please follow along. If you tweet, the event hashtag is #ThisIsCDR. And on to the main event. So please meet Habib. Habib Azarabadi is a Post-Doctoral Research Fellow with Arizona State University's Center for Negative Carbon Emissions. He received his bachelor's degree in chemical engineering from Sharif University of Technology in Tehran, Iran, and earned a master's and PhD in sustainable engineering from Arizona State. Habib's research focuses on environmental and economic analysis of direct air carbon capture technology, as well as positioning DAC technology in the existing energy infrastructure and scaling it through mass production. Habib, over to you.
Hello, thank you for having me. I'm very excited to be here. Okay, thank you so much for the introduction. I'm very happy to be here. So today, as you all know, I'm going to talk about an introduction about direct air capture and more focus on my work. So we all, I assume that we know here that we need to balance the carbon budget. And for that, we not only need to reach carbon neutrality, but also remove some of the emissions that we have emitted in the past. And for that, we would need to remove carbon dioxide from the atmosphere. We know that planting trees and biological means are not enough, and we would need some sort of artificial way of removing CO2 from the atmosphere. And that's where air capture comes into picture. You can see on the left just a schematic view of the technology where you use a sorbent, either in form of liquid or solid, to contact with air at 410 by now ppm, part per million concentration of CO2. And when the sorbent material is loaded, you use energy to regenerate sorbent, to reuse it, and also separate and concentrate the carbon dioxide for further processing. We are past that point that we argue if air capture is feasible. It has been shown that it's technically feasible, and I'm not going to go over that. This was a discussion for maybe 2009, 10, or 11, but I'm going to talk about the challenges that air capture faces today. And you can see that there is the cost of air capture is still relatively high for climate purposes. We are today at Climeworks probably somewhere around $500 or $600 per ton. This is data from 2019 that they announced. And for carbon engineering, they are hoping to achieve a price lower than $200 per ton when they build their larger scale plants. That's still relatively high. It's very promising though. But there is also another issue, which is the small market for air capture. And right now, for example, in the US, the most demand and market for CDR generally is from voluntary market, a big part of it by companies like Stripe or Microsoft. But this is a sort of like a conundrum that DAC is facing today, that the price is too high for a market, and then market never expands unless the price goes down, and price never doesn't easily go down if you don't have much demand. So that's a big challenge for air capture today. And also the need for massive scale up if you want to meet the mid-century goals for CDR. If you want to achieve multiple gigaton CDR level, there will be a huge that will require a huge effort for scaling DAC up, which I'll be talking about it more. So first, I want to ask we try to answer the question that how much does it take to buy down the cost of DAC? And for that, we looked at similar technologies that experienced a massive cost reduction from the time that they were new and emerging until today, that they are deployed in larger scale. And solar is a very good example. You can see between 1975 to 2018, it experienced a roughly 300-fold cost reduction in a graph. The x-axis shows the total cumulative capacity of solar modules produced, and the y-axis shows the cost. You can see that is typically explained by learning by doing. That is just a simple concept that as we do more and we keep building more of a technology, we get better at it, the knowledge advances, and the technology tends to get cheaper. And that's known as learning by doing. This is not a scientific fact. It's just empirical observation that we have observed in many technologies. And we wanted to use the same idea to see how much it takes for direct air capture to experience a desirable cost reduction. And you can see for solar, this is a log basis axis. So you can easily fit a power function into the data for solar PV cost. And that means that for basically that's what learning by doing says, for every doubling in the output, you have a certain percentage in your cost reduction. And for solar PV, that was give or take 20%. But it's a different number for every technology. And you can see here in the equation, just simply showing that the cost of nth unit is equal to cost of first unit times epsilon, which is a factor that is related to learning rate. It's if learning rate is 20%, epsilon is 0.8 to the power of number of doubling. That's what log 2 of n shows. And that's basically the simple idea behind learning by doing. So we looked at solar, and if you pay attention, in the last 40 to 50 years, solar had 100-time cost reduction. As you can see, it's the same data on the graph. And for that, it had a roughly 1 million fold increase in the cumulative capacity. So if we assume direct air capture is today at $500 to $600 per ton, I think we all can agree that 50 to 60 times, 10-fold cost reduction is desirable. for DAC price. And if you assume with the same slope, the cost reduces with the same slope, we have a much easier job for reducing the cost of DAC compared to what we did for solar. And that would only require a 1,000-fold increase in your deployed capacity, I would say, from the today's kiloton level to a megaton level of capture capacity. So we built a model. This is just the model is very equation intensive. I don't want to go over all the equations. So we basically assume our model is very generic. It doesn't consider any specific solid or liquid sorbent because of lack of data and because the technology is very new. So we wanted to keep it generic. So we assume the first DAC unit cost has two components. One is the cost that is subjected to learning. It can reduce over time. The other part is the residual cost. That is mainly the minimum, the bare minimum energy or material that you would need, and that cost is not going to go away. So if this is the cost of first unit, for the nth unit, you will have the C of n. This is the reduced cost for the portion of for the cost component that can reduce, plus R, which remains constant. And you can have the relationship as I showed for the reducible cost like this. So I'm going to go a little bit over details about the model that what it does. This is basically the same graph as I showed for solar PV cost, but this is just on a linear axis. You can see X and Y. On X-axis, you have again the cumulative number of DAC units installed, and on the X-axis, you have DAC price. So for example, the first DAC unit is very expensive, $400, $500, $600 per ton. You can see at the top, but as you build more, the levelized cost keeps decreasing. In unlimited number of units, infinity, you will reach the residual cost. This is kind of what this red curve will, this is an asymptote for the red curve. But we were interested not in the residual cost, but in a target cost as that is between today's price and the ultimate low price of CO2. And that target cost is a cost that typically is referred to as the threshold that if you reach the technology will be self-sufficient. And it would not require as much external support, mainly because there is a market for commercial CO2, that's one, and also ultimately the climate market. We can argue where the target cost is, but typically $100 per ton is a number that you can find out there. And that also makes sense because that's the you can say average commercial CO2, the smallest scale commercial CO2 consumption. In the US happens at this cost at roughly $100 per ton. So that's where we assume the target cost. And we are only interested in buying down the cost of DAC up to this target cost. That was the purpose of this analysis. So if we assume that for every ton that these devices capture, you have a market at a target cost, so you will have a revenue at this level of target cost. Then the only thing that you need to absorb as a policymaker or as someone who has an interest in DAC to reduce the cost of DAC is this part between the red curve and the target line and the target cost line. And you can see eventually this excess cost goes to zero when we achieve the target cost. So we wanted to see what is this excess cost, the hash area. Here, we were interested to find that out. And we also wanted to see how many units of DAC, what is the deployment level that you will achieve that, that target cost and that threshold. That's what we wanted to do. And for that, we needed to basically give a number to our model parameters. If you look at this table, I'm just going to go quickly over some of these. For alpha, which is it has a relationship with learning rate, and epsilon, the progress ratio. We assume 2/3, or for epsilon 0.8 or 20% learning rate, which is almost the same as solar. For the cost component that is reducible, we assume $470 per ton, and for the residual cost, $30 per ton. These together will be 500, which we work with the number that Kleinwork published, announced publicly. And then for target cost, we talked about it, $100 per ton. And these two last parameters, which are important and they have a relationship with learning rate, is the lifetime of every DAC module and its size. Our main assumption in this model was that DAC development will happen on a small modular scale. And that means that instead of building large plants, like a big chemical plant or a big power plant for millions of tons of capture capacity every year, you go a smaller scale with maybe 1,000 tons per year. And going as small has major advantages, including that you escape the locking in the technology. When your technology is very new and it's advancing every day, you don't want to make a large scale and long time investment for several decades to lock yourself in a technology that might be abandoned in several years. It might be just old in several years. So that was our main assumption, to go small and modular. I will talk more about this, and I imagine there will be more questions about it. But this has direct impact on this relatively high learning rate that we assumed in the model. So if we use those numbers, these are the model results. For the excess cost, we get 50 million total. That's a one-time cost to buy down the cost of DAC to $100. For the total cost, meaning that this area under this curve, it's about $200 million. And for the number of units, we got the number around 300 units with 1,000 ton per year capacity, or the total amount of CO2 that needs to be captured to achieve the cost is about 1.5 million tons. A few interesting learning that you can immediately get from this curve is, first, the cost is not all that high. If you compare it to other form of support for different low carbon technologies, for example, an example is point source capture, the Petronova plant. The Department of Energy alone spent around $1 billion on that project. And also you see the subsidies from different sources, the state or federal, that companies like Tesla for electric vehicles, they get, it's definitely orders of magnitude higher than this number. So that was one important learning. And the other one was the number of units and the total amount of CO2 that needs to be captured. That's certainly within the amount of CO2 market that we have today in the US alone. In the US alone, we, I believe, consume about, I think more than 1 million ton a year for only beverage and food applications, carbon dioxide. So that's certainly a market that you can enter to buy down the cost of DAC. So this was the uncertainty analysis for the model, because a lot of these parameters, there's just so much uncertainty and the technology is so new. So we thought it's very important to just play with these numbers and see how the results change. So the main part was the learning, the alpha, which represents learning. We assume the alpha 0.44 to 1, which basically 1 says no learning, almost no learning. And 0.44 is roughly 30% learning rates. And also you can see for the reducible cost and residual cost, we have this value, this range that we fed to the equation. This is the equation for excess cost here. So we basically had a distribution, we had a Monte Carlo simulation, a distribution of each one of these variables, and just calculated the result with this distribution. And this is the final results for uncertainty analysis. This is a cumulative probability distribution plot. And let's focus on the solid line for now. This says the x-axis is the excess cost, the amount of money that the amount of investment that needs to be absorbed to buy down the cost to $100 per ton. And the y-axis is the success probability, basically within the limits of our model, within all the scenarios that we simulated. So you can see roughly for, if you spend 100 million, roughly 50%, you have a 50% chance to achieve that $100 per ton. And if you go up to about $2 billion excess cost, which is still not a large number, you have a 90% chances of reaching that $100 per ton price, which is very promising. So our main argument was that this is not a big investment. If you spend this much money on buying down the cost of DAC and maximize learning, you will either find out that, yes, this is a promising technology and it's going to help, and it will cost, and it will significantly help us with climate change, or you will find out, yeah, this is a failure and the cost is not going down as much as we expected, which could very well be the result. But it's very unlikely according to the model. But it's an important question that this relatively small investment can answer. Now that we've found out how much money needs to be spent to buy down the cost, I'm going to go over how we should spend this money and what is the right strategy to buy down the cost of that. This is a new work that Klaus and I have been working on, and this is a paper that has not been published, so I'm very excited to share these results here. So it's certainly time for deployment. The research and development and demonstration is absolutely important, but it is time to build actual DAC units and have DAC projects in the pipeline to observe this cost reduction, to see if learning is happening. But that needs to be done in a certain way. And these are the important criteria that we think has to be observed. First, the learning should be maximized. You need to maximize learning. And that can be done in several methods. First, as I argued, the small modular DAC units, which they have shown a higher learning rate. That's a big thing, especially for a technology that is new. Initially, you might think building large units allow you to take advantage of the economy of scale, and that is true. That's what carbon engineering is doing. But down the road, I believe there's a very high chance that mass production of a small modular DAC units can beat that and provide a low-cost DAC. You can have cost reduction in 3 cost components. That's how I like to break down the cost of DAC. First is Sorbent. There's a lot of opportunities for innovation in Sorbent. There are so many new approaches. There are metal organic frameworks which are very promising. There are methods like the electroswing and other sorbents that have shown very promising results, but they're not there yet. Energy consumption, you can use passive capture. I think that's a huge advantage, that if air capture companies stop using fans to blow air, I think that can in the long run significantly reduce the cost. Also, we are far from the thermodynamic limits of CO2 air separation energy requirements. So there is a lot of room for improvement in energy consumption. And finally, the balance of the plant, those areas that you wouldn't think that there will be a lot of learning, for example, in compressor or in building construction site. But what's interesting is that there has been learning observed even in those areas for solar PV. For example, there has been learning in the structure that holds solar PVs. We thought we need to have a concrete pad to hold our solar PVs, but today we know that's not necessary. And all of these are different way of lowering costs and basically trimming the amount of materials other than solvent that you hold into your system. Automation for sure can reduce the cost. That includes using automation for operating or finding the lifetime of sorbent, because air capture performance is dependent on the weather. So automation and machine learning can certainly help with that. And finally is knowledge spillover and open source research. Knowledge spillover is very important, but a policy or support framework needs to be careful that it's important to allow a little bit of knowledge comes out and accelerate the overall learning in the community, but you also need to keep innovators and technology developers interested in innovation. So that's a very delicate one to deal with here. And also open source research communities like OpenAir, which they do a fantastic job in, especially in areas like sorbent development, having open source research or publishing data for sorbents, it can in the long run be very helpful and accelerate sorbent development, even with methods like machine learning or deep learning. When you have a big database of sorbents, you can go and see what desired feature are related to a synthetic method or in a specific sorbent structure. You can find those nonlinear relationship with these deep learning algorithms, and that can certainly accelerate the sorbent development. It's very important to encourage competition and price discovery. Price discovery allows you to observe learning. It's important to see if it's working and if the price is coming down. If you have a few players that they protect their price, that is not going to happen. That will be very difficult. So it's important to have a competition. It's important to avoid an oligopoly where a few companies are certain that they have a big share of market and there's no other competitors. That can certainly damage the technology and it can reduce learning for sure. So that one is certainly one of the important ones to encourage in a policy. Lower the risk of investment. Again, going small and modular allows the small and new players to get involved because there will be lower risk for them. Creating a reliable market like the power purchasing agreements, that's for sure is very important and can help incentivize investors to enter the market. And also engaging niche application, as we argued in our paper, can certainly lower the cost of technology, the cost of subsidies that need to be provided. And spoiler alert, I believe reverse auctions can do that. And this is what we have been working on. Basically, reverse auction has been used for renewable technologies for many years. And it is also called demand auction, where you have an auctioneer, which is typically the government, which put out a demand, and technology developers come and bid for that demand, and there is a competition for sure. And it provides a lot of remarkable flexibility to engage all of these important parameters that I discussed here into learning. We are working on a paper that tailored auction for the current state of DAC development, and that will be out soon. So just a few final thoughts. I think we are at an inflection point. It's very important. There will be a lot of money in this in the coming years, but I think that also comes with responsibility. We need to make sure we don't repeat the same mistakes that happened for 15, 20 years ago in the clean tech boom in the United States. It is very important to avoid those. I think we need to start implementing, and we need to observe if learning by doing is happening. If we say technology, if you look at this graph on the right, if we say DAC is here at this line where we pass the innovators phase and we are starting early adopters, I think we need two separate strategies in the coming decades. First, we need one strategy to get to the megaton scale. And for that, we have to maximize learning. And that's a separate plan than for reaching the gigaton scale for climate change. As far as I'm concerned, this might be controversial, but even if you capture CO2 and release it to the atmosphere on a megaton scale, but you maximize learning, that will be still desirable. Because a megaton scale is not going to significantly contribute to climate change problem. California alone has like 500 million tons of CO2 emission every year. So it's very small, but it can certainly be important for reducing the cost. And finally, as David Izikowicz, he argues in his new paper, which I recommended to everyone, when we achieve the cost reduction that is desirable, when we observe reducing costs, we need to have that wartime level of efforts to achieving the gigaton level and basically pass this early adopter phase to achieve the goal that we need by mid-century for CDR. Yeah, thank you for your attention.
That was great, Habib. Thank you so much. Lot to unpack there. We have a few prepared questions, and then we have a ton of audience questions, which is fantastic. Thank you all for your questions, and please continue to submit them. A couple of these questions you touched upon in your presentation, but I think it would probably be beneficial to maybe review a couple points. So modularity obviously is a big key to these successful cost and learning curves. And we saw it with solar, and the thesis is that we will see it with direct air capture as well. I believe Chris already put a link to Naeem Merchant's blog in the chat, but he wrote a recent post drilling down into modularity. And I think it was he very helpfully broke out 3 types of modularity that can potentially help scale DAC. So number one, as kind of it seemed like you focused on a little bit, the small self-contained units versus the large unitary industrial scale plants. Number 2, within whatever size DAC unit, having modular plug and play components so that they can be manufactured broadly and there can be competition to manufacture and everything's not bespoke. And then number 3, I thought was very interesting, modularity in terms of business model. So I do think that there are a number of early stage DAC companies out there that are trying to potentially do too much, and maybe if they focus on one piece of the value chain and then let someone else specialize in sequestration, let someone else specialize in transport, etc. I don't know. What are your thoughts on that kind of general breakout? Does it make sense to you? And also, are there other aspects or dimensions of modularity that you think are important to be considering?
Yeah, I read the article that Naeem wrote, and I totally agree with the points that he makes. Very valid points. And I would like to argue it this way, that we used to go larger scale with our power plants, with our chemical plants and all of that to take advantage of economy of scale, but also it was important to lower labor costs. Right now, today, with the level of automation that we have, that doesn't seem necessary. And that provides a huge opportunity for going smaller scale. One important, interesting analysis that I like to mention, and Klaus always mentions, was that if you compare a power plant with a car engine on a kilowatt to kilowatt scale, car engine is 100 times cheaper than a power plant. And the reason is that we don't build as many power plants. And for every power plant that we build, it's pretty much a custom-made plant unit. There's no mass production, but car engines are the exact opposite extreme, that you just have these factories and mass production. And I agree with the point that Naeem makes, especially in terms of diffusivity. If you go smaller scale, it also opens a lot of niche applications that a larger scale CO2 plant might not necessarily have. And you can take advantage of those markets, which helps you, as I discussed, with cost reduction. So yeah, certainly there's a lot of opportunities. And I believe at this stage, at least, it's very important to take advantage of small modular units. And that might change down the road. When the cost is low, we might say, hey, it makes sense to go large for DAC. But I think at current stage, it's important to have these new generations of DAC units and lower the cost by maximize innovation, basically. Yeah.
And do you think, just one follow up there on so, going in terms of going big, you could build a large unitary DAC plant, but you could also build a complex of modular DAC units, correct? Those are kind of two separate approaches. So maybe you can still go big while maintaining some of the advantages of modularity, or do you think that eventually you're just going to want to go big? Or hard to say?
There was this new paper that it kind of broke down the impact of learning into not just size, but also the complexity of the model, like how many components your system have versus, and also how custom made your system is. Like these are the two factors they looked at, and it was very interesting. So if you look at DAC is not completely custom made, but you might need for different climates, but there is a high chance that you would not need to build custom made units. So I guess you can take advantage of going large there, but if you go large, I think it naturally happens that your systems become more complicated. Especially, this is one thing that Naeem argues, that if you want to do plug and play, if you want to have other systems following your DAC, for example, fuel production. I think that certainly increases the complexity and the number of components that your system has, and that lower your learning rate.
Very good, thank you. You talked quite a bit about Sorbent, and so there's obviously a lot of opportunity for innovation with Sorbent. Do you think that and one thing that we've noticed kind of about the various different tech pathways that are in development for direct air capture, there's a wide range of sorbents being used, some of which seem to be a lot more widely available and commonly available, and others seem to be a little bit more either engineered or relying on materials that are potentially a little bit more scarce. Whether it's, like a heirloom that's using calcium or magnesium oxide, and then maybe some of the other ones are a little more rarefied. Do you think that's an issue? Do you think that there's certain DAC pathways that might run into scarcity issues with respect to sorbent that would keep them from scaling effectively?
It could, yes. Some materials, especially some very advanced materials, as you mentioned, they could be either scarcity or the cost reduction is very slow. We don't see a large scale production today, and it's very expensive. Like metal organic frameworks are in that group, that they might end up being expensive and difficult to lower the cost. At the same time, I think it's very important to keep that door of innovation open, because we have seen cost reduction happening with technologies that we didn't expect. So it's very important to have an open mind and allow these new sorbent materials and these new technologies to just move forward, be implemented, and then see. I think it naturally, the mass production and larger scale naturally follows that. And if the market finds out that that's not doable, then I think they will just die over time. And if the effort, is inferable.
Speaking of innovation, it's super exciting time to be thinking about DAC, I would say, just because there's so much innovation in the space. I mean, a new company that's been around under the surface for a while, but just kind of went public yesterday with their at least high-level method, Heimdall, that uses an electrochemical approach to store CO2 and water, and then elicit a carbon negative cement. You've got sort of the incumbent sorbent and liquid solvent approaches represented by Climeworks and Carbon Engineering, electrochemical from Verdox, Holy Grail, and others, and novel scaling of mineralization from Heirloom. Do you have any personal kind of, which of these pathways do you can you speak to one of them that you find particularly exciting, sort of in general and also from a scale potential perspective?
I believe there are several sorbents that are very, very interesting, and they offer a lot of opportunity. One is for sure metal organic frameworks, and particularly what we find interesting, and we have been just thinking about recently in our group, is this step function sorbent that Jeff Long at UC Berkeley with metal organic frameworks. They just show very interesting behavior that they can be potentially very useful for DAC and lower the cost of regeneration. So that's definitely one area to look into. The other one is membranes. There's a lot of hope with membranes, and you can see some very desirable permeability and selectivity behavior in recent development in membranes for direct air captures. So that's another area. And also there's more creative areas that they are just entering the market. And one of them is one of my friends, and he was a former student of Klaus, started this company. It's called Aircella, and they basically couple electrolysis for hydrogen production with air capture, and that offers a huge advantage of basically producing hydrogen and oxygen as a byproduct, and couple air capture with fuel production, which I think that's also very promising technology.
Can you repeat the name of the company or spell it out so we can put it in the chat?
It's air. It's like air, like Aircella, C-E-L-A, Aircella.
Aircella. Okay, cool. We'll look it up and put it in the chat. I'm actually not familiar with that one, so that's very interesting. Thank you. So one last question from us before we kick it over to the abundant audience Q&A. Back to the policy question that you sort of closed with, and this will be a little bit of a repeat, but I think it's worth emphasizing. So we are very keen at OpenAir on policy development for at the state and local level. And there's a recent paper that you mentioned and that we talked about a little bit by EDF that talked about a federal procurement policy built around a reverse auction mechanism. And we're also very keen on this idea of a reverse auction mechanism for the reasons you stated, because it provides a little bit of control, but also allows for some price competition. What are your thoughts on, there's voluntary procurement out there, and that's the primary market for all of carbon removal right now. What is your thought on the role of the government, and in particular state and local government? Do you think there's an opportunity there, and how do you feel like that could play into helping to scale both direct air capture and then other kind of more carbon dioxide removal more broadly?
Yeah, I believe if you look at the example of renewable energy, renewable electricity, solar and wind mainly, auctions are becoming exceedingly popular. And I think there's a lesson to learn from there. The main reason is that auctions are very flexible. And if you look at the countries that they have used auction for renewables, there's a wide range from developed countries like Germany to developing countries in Africa, that they have taken advantage of auctions because of their remarkable flexibility. You can just tailor auction for applications that you need. And like you said, the competition and price discovery is one of the most important features that we can find useful here for air capture. I believe if we all agree that small modular DAC is the way to go, I think there is a way to design auctions that exactly pursue that. And also there is a way to just maximize learning for sure, and also allow for a little bit of knowledge spillover by designing your auction in a way that allows for that. So basically all the components, all the important parameters that I talked about in that slide, I think you can, and we have been working on that. You can use that in early auctions, and they also offer the flexibility to use the same policy or investment tool, I would say, as the technology matures, and then you would need to change approaches. For example, it becomes important to look at the permanence in your storage. Well, how do you handle the CO2? That might not be important at the beginning, but it's certainly important at the when the technology becomes more mature and you want to get to the gigaton level. And auctions also allow you to have a parallel competition on the CO2 handling side, which is amazing. And you see in renewables, by the way, that there's not only competition to get the project to get for just build, for example, a wind farm, but also there is a competition between the sites that they want to get that project. So that's very amazing. And I think that you can take a lot of advantage of this form of auctions for generally CDR, but also air capture, what we have been more.
That's great. I love the emphasis on price discovery. And I think, for example, the transparency of Stripe in their CDR procurement has been super beneficial for the entire sector. And just a quick plug, OpenAir will be premiering a CDR policy for New York State called the Carbon Dioxide Removal Leadership Act later this fall, and it is built around a reverse auction mechanism. So we're kind of excited about that, and you'll be hearing more. That's enough of our prepared questions. Megha, do you want to take the reins here and ask some of the audience questions we've been getting?
Yeah, absolutely. So one of the early questions we got was just thinking about essentially the life cycle analysis. So how, when it comes to DAC, how do we make sure that you capture more than you emit? How do you think about like measuring and sort of calculating that?
There have been a few papers recently published, and one of the important components that these papers focused on was the source of energy. And I believe one of them was looking at Climeworks technology, and you basically cannot do that unless you have a certain level of clean energy. like certain level of, there is a threshold for carbon intensity of your electricity to be able to utilize that for DAC. And that of course, it is very important, but also you look at other components that you use, such as cement, steel, and one area that it has not been as much focused on is how you handle the sorbent when you're done with it, when at the end of the life. And that's one area that it significantly can become also an issue as you scale up the technology, as we can see right now, for example, with wind turbines, that there is an issue, how you handle them, how you handle the material when you're done at the end of the lifetime of the technology. So I believe all of these are important to look at, especially when you look at the scales and the amount of electricity, cement, and steel that you would need at that gigaton level. For example, this paper, this recent paper about Climeworks process, they estimated that there will be 1% of total electricity generation will be required to capture 1% of emissions in 2030 by DAC. So that's a significant ratio, and that's just for 1%. So yeah, these are the impacts that we need to think about right now as we are scaling, as we are just considering that a scale up to a gigaton level.
Makes sense, yeah. And you were mentioning, I guess, some considerations around sorbents, and we had a couple of questions around those, which are a bit more technical. So the first one is, do you see any drawbacks for using calcium oxide as a sorbent? And assuming we use calcium carbonate tailings, which has close to zero cost and no additional CO2 impact, and calcination energy with renewables?
Yeah, the main issue I would say is just you're far from the thermodynamic limit, so you have to spend a lot of energy for sure. And if your energy comes from a renewable source, then that's a different discussion. But at the same time, you have to see the capital cost of your unit. Can you utilize renewable energy 24/7? Probably not at the moment, at least. So it's important to see if your capital cost of your calciner units and the rest of your process, if you will not have issues in terms of using only renewable.
Yeah. Yeah, another question on the sorbents was, to what extent do you think we'll need to standardize sorbent materials or technologies to accelerate the scale up, and kind of making the comparison, as you did, to photovoltaics, with polysilicon being kind of the de facto material that brought down the costs and helped scale up in that sector?
I don't think if there is a need to standardize sorbents. There certainly, we need to consider a safety and environmental consideration. That is an area maybe we need a standardization. So because a lot of these sorbents, for example, they might have volatile components, especially if you're a solid sorbent. So, or if you're using a very strong base, it's very important to consider all of that, especially in larger scale, and standardize that. At the same time, standardization at the end of lifetime, how you handle the material. These are important, but I don't see if there's a necessity for limiting the technologies by making that a standardization.
Yeah, cool. And which of the different DAC or DAC tech options do you think is going to have the fastest rates of like learning by doing, as you were talking about, and why, since there's a few out there?
We talked about small modular. I think that's a big one. So compare Carbon Engineering and Climeworks. Carbon Engineering is planning for the second, like the largest scale plan, but Climeworks has already had several generations of their technology. So I would say that's the biggest one as far as we continue. But what was the other part you mentioned? Sorry.
What was the other part? I think just essentially, why do you see certain ones being quicker than others? But I think.
Yeah, just I would say one big one is a small modular. And I think it's too early to say, because the technology is so inefficient right now that we can't say which one is eventually the winner. We need to give more time to see which one, like basically squeeze the most cost out of their plans. Yeah, that needs more time, I think.
Yeah, makes sense. And I guess related to that, someone asked, do you see any insurmountable limitations to the existing tech so temperature, pressure, moisture swing, that will prevent things from coming down to below $100 a ton? Or do you think potentially emerging approaches like electroswing or anything else might actually improve the cost effectiveness and maybe needs a bit more investment to get it there?
I think one big challenge for advanced sorbents such as electroswing is the cost. I think right now they're not there yet, and it's important to see when they can get there. So that could be one limitations on those. Same thing with the metal organic frameworks. So this is something, if you want to get to a gigaton level, for sure, you need to consider all of that. But other than that, among like different sorbents that are out there, I don't see any limitations at the moment. Doesn't come to my mind right now.
Okay, cool. And then with one last question. So someone mentioned, we've talked about large investors like the government kind of accelerating this. What do you think is the utility of individuals purchasing offset from Climeworks or others? Is that a meaningful contribution, or what can the rest of us who are interested in this actually do?
Yeah, I think of course it's important, and it is important to support these companies. That for sure contributes. I mean, Climeworks has a number of supporters, the pioneers on their website, and I think if you account for that, that is significant. At the same time, I believe if we want to have a serious effort, we need to have larger scale investment, either by government or by a private company who has the interest or the will to do that. As we worked out in our paper, that's not a large amount of money relatively. And I think it's important to keep in mind that there needs to be a competition, and pouring billions of dollars into a few companies is a very risky gamble.
Right. Okay.
That's the biggest thing, yeah.
Great. Habib, thank you so much. I really enjoyed hearing from you on this. I'm going to hand it back to Toby to just close this out and finish things off.
Habib, thank you. That was really fantastic. Really appreciate the time and the great presentation. Next week, we have another great and pretty technical presentation from our neighbor in Stony Brook, Long Island, Dr. Matthew Eisenman, who's going to tell us about CMATE. And so first of all, he's going to teach us a little bit about the oceanic carbonate cycle, and then talk about his research into a new technique for ocean alkalinity enhancement, and that also includes carbon dioxide removal. And we'll be continuing these weekly through the end of the year and into 2022. So, please check us out. There are links to the series in the chat. There are links to OpenAir in the chat and to our Twitter. You can follow us on Twitter, and on OpenAir, there's quite a bit on the website, and you can join our Discord via the website. We're an all-volunteer organization. Everyone you see here on this presentation today is a volunteer, and we'd love to have you join us. But thank you again to Habib. That was really a fantastic presentation. Thank you, Megha, and thank you all for joining.